Hello everyone, welcome to the 32nd lecture for the NPTEL course on computer system for machine learning. Today we will have a brief recap on whatever we discussed in the last lecture, and then we will talk about chunked pre-allocation, which is Sarthi. So, in the last lecture we talked about ORCA, which proposes selective batching. If you remember, ORCA first proposed iteration level batching instead of sequence level or maybe request level batching, but then we saw that not every operation in the LLM can be batched, right. So, whenever we have this linear matrix multiplication or linear operation, that can be batched. Whenever we say linear, that so this QKV linear is nothing but whenever we do QWQ, KWK, VWV, so these are linear operation, okay. But in attention, if you remember, in attention we have this softmax operation, correct. So, since softmax is not linear, we cannot do batching. I mean, we cannot like coalesce those matrices and then operate on that, okay. So, that is why ORCA proposes this selective batching, where we can merge multiple inputs to perform QKV linear, then we can split, and then we can perform attention on each input separately. Remember, I mean, intuitively we cannot batch the attention, because if we do perform like batching on attention, then we will end up computing attention for one input with respect to another, right, which we do not want. We want to compute self attention, we want to compute the attention for that particular input itself, correct. Now, after we do the batching, then again we will merge and then perform this linear operation, which is like up projection and down projection, all those things, correct. So, that is what we discussed in the last lecture. We also discussed about like different types of batching or different types of scheduling. We discussed about prefill prioritization as well as decode prioritization, and then we saw that there is no perfect solution. Like some solution may reduce the latency, but then at the cost of lower throughput. Some solution may gain higher throughput at the cost of higher latency or the higher time to first token. So, remember, like just reducing the average latency is not sufficient. We need to see whether the service level objectives like the time to first token or time between token are satisfied or not, because remember that those are the metric which users care, okay. Now, let us discuss about chunked pre-allocation. Sarthi is the paper. Please go ahead and read the paper thoroughly. So, today we will have a brief overview of Sarthi. Sarthi mainly proposes something called chunked pre-allocation. Now, let us see the throughput the scheduling trade-off. So, there exist many techniques, right. I mean, Sarthi is not the only technique. So, let us see where different techniques fall. So, here x axis is time between token, which is nothing but latency per token, and y axis is throughput, queries per second, okay, how many queries are being served per second per unit time, correct. So, there are techniques like faster transformer, which prioritizes the decode, and then if someone or if some technique is prioritizing the decode, then time between token will be low, because again prioritizing decode means we will generate the decoded tokens at a very high rate, correct. But then throughput will be less, because remember, if we prioritize the decode, then prefill is stalled, right. So, queries per second, how many queries we are able to serve per second is low, okay. Now, then there are techniques like ORCA or VLLM, which is prefill prioritizing. If we do prefill prioritizing, then queries per second is high, but the user experience is bad. When I say user experience, the time between token is also high. That means, let us say some decode is going on, and then during that ongoing decode, if there is a new prefill launched, then ORCA or VLLM will prioritize that new prefill. Now, in that case, the decode is stalled, the previous decode is stalled, and that is why this time between token is higher, right. There is a technique called light LLM, which provides dynamic priority between the prefill and decode. It kind of like tries to strike a balance between time between token and throughput, but again not too much. So, our ideal region is here, right. so means throughput will be very high, and then the time between token will also be very low, correct. So that is the ideal scheduler. So we should have an ideal scheduler which has higher throughput, like queries per second should be high, and time between token or the latency per decoded token should be low, right. So existing system compromise on either throughput or latency, correct. Now we can actually perform mixed batching where we combine the prefill and decode computation, correct. So let us say we have decode latency service level objective is 10 millisecond. Again, when we say service level objective, that means user is okay if the time between token is 10 millisecond, but not more than that, okay. Now what VLLM does is, let us say the decode is happening of a query A with latency 8 millisecond. Since it is a prefill prioritization, since it prioritizes prefill, that means if some other prefill, if the prefill of some other token other request comes, then VLLM will continue with the prefill, right. After the prefill is over, then the VLLM will be performing this decode of A and B together, correct. Now here the problem is, since the decode of A was stalled because of this prefill of B, that is why the second token of the next token of next token of A got generated like later. So it got generated at 24th millisecond. That means the time between token is 16 millisecond, which definitely does not satisfy the service level objective, which is 10 millisecond, right. So that is VLLM for you. Now what we can do is, we can perform the decode and prefill of B, decode of A and prefill of B together, and then let us say here the latency was 8 millisecond, and then we finish the decode plus prefill at 16th millisecond. So here of course we have, I mean the SLO is satisfied, right. Here latency is 16 millisecond, right. Now sorry, the latency is still not, the SLO is still not satisfied. Okay, I told you something wrong. I mean when we say decode latency SLO is 10 millisecond, that means within 10 millisecond things should be over, okay. I mean we have to things should be over means the total latency should be 10. So when we say 24 millisecond, this entire thing is not 16 millisecond, this is 24 millisecond. So that is, I mean that does not satisfy the SLO. When we say latency equals to 16 millisecond, this whole thing is 16 millisecond, which is again greater than 10 millisecond. So again, I mean it violates the SLO, it violates the service level objective, right. I mean although we mixed this prefill and decode, but still we are not able to hit this goal of this SLO of 10 millisecond, right. And why? Because the high latency is occurring due to combining the large prefill with the decode, right. Now this particular figure is showing the batch time of decode only versus decode plus full prefill. So if the decode, I mean if you see, look closely, I mean if we increase the batch size from batch size of 1 to 32 to 64, the increase in batch time reduces, I mean although reduces, but still I mean if we do decode plus full prefill, then the batch time, I mean the time at which the whole batch will be finished is much more higher than decode only times or decode only latencies, right. Now so far we have seen that if we do prefill prioritization, then if we do prefill prioritization, then maybe we will satisfy the queries per second SLO, or we will have higher throughput, but then the decoded tokens will be generated at a lower rate. That means the time between token will be higher. If we prioritize the decode, then the time between token will be lower, the decoded token will be generated at higher rate, but since we are pausing the prefill, we are stalling the prefill, we will have lesser queries per second. Now we can mix this prefill plus decode, but that also does not help, right. Now from this, Sarthi had a good intuition, it had a good key insight of chunked prefill. So, the main idea behind Sarthi is prefills can be split into smaller chunks that marginally add to the decode batch time. Okay. So, that means instead of launching the whole prefill with the decode, like I was showing in the previous example here, in the previous example we were launching the whole prefill with the decode. Instead of doing that, instead of launching the whole prefill with the decode, we can chunk the prefill. Okay. Again, prefill also have, I mean, we can do either tensor, I mean chunking by the tensor or data or something. But at the end of the day, if we chunk the prefill, if we segregate the prefill into smaller computation and then launch those chunks so that it marginally add to the decode batch time. So, that will again, that will not affect the decode batch time. That means the time between token will not be affected, but at the same time the entire prefill is not stalled, right? The prefill is still going on, correct? So, that is the key insight behind Sarthi. Now, before we delve deep into Sarthi, let us talk about this arithmetic intensity. So, what actually Sarthi does, it exploits the arithmetic intensity slack. So, I hope you all know about this arithmetic intensity. Arithmetic intensity is nothing but flops per byte. So, flops is floating point operations per byte, means per byte of memory accesses how many floating point operations are being performed. Okay. If we access 1 byte of memory and then with 1 byte of memory if we are performing 10 floating point operation, then our arithmetic intensity is 10 over 1, which is 1, sorry 10, right. So, that is arithmetic intensity, flops per byte, and the y axis here is flops per second, means how fast we are performing the computation. Okay. Now, so usually if we have, I mean for any processor, this is called the roofline analysis curve. This roofline analysis curve looks like this. So, initially with higher, I mean if we increase the arithmetic intensity, the performance also increases. Like when I say increase the arithmetic intensity, means if we perform more flops per byte, if we perform more flops per byte, then the flops per second also increases, but then after some time it saturates, the flops per second saturates. So, whenever the flops per byte is more, that means the whole operation is memory bound, because this denominator is actually dominating, right. So, that is why the flops per byte is more. So, that is why this part of the curve is memory bound, but after some time it saturates, after some time the curve saturates, then we have compute bound. That means even if flops per byte, I mean per 1 byte of with 1 byte of memory, the number of operations are increasing, but then we do not have that much capacity of the compute unit to perform those much operations per second. Okay. So, the performance is not increasing, right. So, that is why this part of the curve is compute bound. Okay. So, we have to see, like again, this is the curve for one particular system, let us say one particular GPU. Now, if we run different applications will fall onto different part of this curve, right. Now, whenever we say application, we mean some algorithm, some processing, some algorithm which is performing some arithmetic operation, right. Now with that, let us see how decode and prefill, or where do decode and prefill operation of these LLM fall into this picture. Okay. So, when we say decode, again let us assume that we have KV cache, right. If we have KV cache, that means for any of the decoded token we have exactly same amount of computation, right. But then for that amount of computation, and then when we say same amount of computation, that is just for one, that computation is if you remember, that computation or the matrix sizes were just 1 over d, like Q, K, V matrix sizes were 1 over d, right. Now, that computation, that amount of computation is much lesser compared to the memory access. Now, whenever we say memory access, remember we are talking about the number of weights or the amount of weights which we access, right. So, for any decoded tokens, we need to access same amount of weights, correct, and same amount of weights plus the KV cache, right. So, remember the KV cache size increases as we increase the sequence length, correct. So, this for decode the memory access dominates, correct, because our compute is less, memory access dominates, that is why it falls into the memory bound region of the roofline analysis curve. And again, I mean intuitively you can think that the denominator, this number of byte, the amount of byte is very very high for decode, so flops per byte is less, correct. So, that is why and then again we will like the performance is also less, because when I say less, that means the number of flops is itself is less, right. So, that is why decode falls into this part of region of the roofline analysis, correct. Now, if we talk about prefill, so while doing the prefill, remember we have to analyze a sequence of we have to analyze the whole prompt, right. Now, that prompt contains of many tokens, it is not just one token, correct. So, that means the amount of computation is high. So, this is for decode, like for decode QKV matrix size is always 1 by D, but for prefill the QKV matrix size is like n by D, correct, where n is the prompt length. Okay. So, if n is the prompt length, then you can easily see that the number of computation or the amount of computation in prefill is much more higher than decode. But when we talk about the memory access during prefill, first of all there is no concept of KV cache, like we do not need to fetch any KV cache from anything, because that is the first time we are going to compute. So, there is no KV cache, one thing, and second thing is the amount of weight is exactly the same as the number of weight or the amount of weight needs to be fetched for decode. Okay. Of course, I mean for some specific case, maybe MOE and all, maybe the amount of weights fetched for prefill and decode is same, but we are talking about the regular transformer based LLMs. Okay. So, as you can see, prefill has higher number of compute, the amount of compute is higher and the memory access is lower, right. Why memory access is lower? I mean when we say higher or lower, it is compared to decode. Okay. So, amount of compute with compared to decode is higher, because prefill has to analyze the whole prompt, not just single token, right, and one prompt will have many tokens, that is why number of computation is higher. Now, the amount of memory access during prefill is lower than decode, because during decode we have to fetch the weights. Now, we have to fetch the same weights for prefill also, but in decode additionally we have to fetch the KV cache, right. Again we have to fetch the KV cache again and again from the memory while we are decoding the token, right. Now, that KV cache is not there for prefill, because we are generating the KV cache for the first time during the prefill. Okay. So, that is why the amount of memory access is less, because there is no KV cache for prefill. Okay. I mean again if we do prefill by chunking or something, maybe there will be concept of KV cache, but if we do the whole prefill together, then there is no KV cache. Okay. So, that is why prefill falls this region, in this region of the roofline curve, where we can see that the entire prefill is compute bound. Okay. Now, Sarthi actually strikes a good balance between prefill and decode, or I mean it tries to push some more compute with decode, so that both prefill and decode operates in this region. Okay. We will see very soon, but the beauty of this is if we are like at the knee of the curve, like if our arithmetic intensity is less and the performance is less, that means the utilization of the core or the utilization of the GPUs are also less, right. Now, on the other hand, if we are at this part of the curve, that means we are like stressing the GPUs more than its capacity, right. So, that Sarthi does something which we will soon see. which strikes a good balance between arithmetic intensity as well as performance. Okay. Now, another observation is the arithmetic intensity slack. So, similar to previous curve, but let us see. So, in the previous one I showed you like in general how this performance versus arithmetic intensity look like for prefill and decode, but now let us see what happens as we increase the sequence length or as the number of tokens increase. So, this particular figure is showing the arithmetic intensity flops per byte, the x axis of the previous curve versus the number of tokens, right. Now, again if we are in the bottom half of the curve, then we are in the memory bound region. Why? Because again, as I already told you, if the flops per byte is less, that means this memory access, the number of memory access is dominating, or this flops is less. You can think anything, right. That means it is a memory bound region. Now, if flops per byte is high, then the amount of compute is dominating, correct. So, that is why we are in compute bound. So, the bottom half of the curve is memory bound and the top half of the curve is compute bound, right. Now, let us see what happens when we increase the number of tokens. If we increase the number of tokens, then remember so again when we are in this part of the curve, the latency is dominated by the weight fetching time. So, that means we are not performing much computation, but we are performing or we are accessing lot of data or we are accessing lot of memory. So, that access is actually dominated or the latency is dominated by the weight fetching time, right. Now, that is kind of independent of number of tokens, because remember if we are decoding, then I mean for every decode token the amount of weight is same, exactly the same, right. So, that is why that the weight fetching time is independent of number of tokens, because we need to fetch exactly the same amount of weight or exactly the same number of weights irrespective of whatever is my number of tokens, right. Now, the top half of the curve is the place where latency is dominated by the compute. Now, that part grows linearly with number of tokens. Again, remember the compute increases when the number of token increases, right. It may be for prefill. Okay. Remember in the prefill, whenever we have more number of tokens, then our latency can be dominated by the compute, because for more number of token all the matrix sizes will be higher. So, we will have more matrix multiplication or more multiplication, addition, operation, etc., right. Now, prefill comes here. Of course, you can imagine that prefill has higher arithmetic intensity. During prefill we perform more flops, more compute, we perform more compute than we have more compute than the number of or amount of memory access we perform, right. Again, as I was saying, that amount of memory access is independent of number of tokens. Now, as you can expect, decode comes somewhere here, because decode has less arithmetic intensity. If we have KV cache, then the amount of compute is like exactly the same, but the amount of memory access is high, correct. Why the amount of memory access is high? Because remember for decode all the matrix sizes is 1 over d, like all the QKV matrix sizes is 1 over d if we are having KV cache, but then the amount of weight is very high, right. All the weight matrices are of size d by d, correct. So, if we see this arithmetic intensity versus number of token curve, so prefill comes in the upper half of the curve and decode comes in the lower half of the curve. So, that is another observation, that we have a arithmetic intensity slack. Now, again in Saarthi, the authors tried to bridge this gap. So, they tried to push some more computation during decode, so that the arithmetic intensity improves, and then they chunked the prefill, so that the arithmetic intensity of prefill is less, so that the performance is improving. Okay. So, that is the main goal of Saarthi. Now, let us Now let us see how actually the Sarthi works. So, we already saw that, let us say we have the service level objective of decode is only 10 millisecond. Now, the baseline is VLLM, which is a prefill prioritized policy, prefill prioritizing policy. So, here the decode of request A was going on, and then the prefill of B is scheduled. So, since it prioritizes prefill, that is why it schedules the prefill of B, correct. That means it stalled the decode of A. After the prefill of B is over, then both decode of A and B can move on parallelly, right. But then this whole time is 24 millisecond, which is much greater than 10 milliseconds. So, it cannot satisfy the service level objective, right. Now, we can push the whole prefill and decode together, but still, since we are computing this whole entire prefill and decode together, the latency accumulated or the latency incurred by this whole prefill and decode is 16 millisecond, which is again greater than 10 millisecond service level objective. So, it cannot satisfy the service level objective in this case too, correct. In Sarthi serve, what is being done, instead of scheduling the entire prefill together, the author chunks the prefill. So, the author, again we will see how to chunk and all those things, but you can think that it doesn't launch the entire prefill computation, it doesn't launch the entire computation during the prefill, rather it cuts the computation, and then with that chunked prefill it schedules the decode. Okay. Now, that means we are reducing the arithmetic intensity of prefill, because the number of floating point operations are now lesser for BP1. So, BP1 plus BP2 is BP, okay, let us say. So, that is a chunk, these are the chunks. Okay. So, here we are reducing the arithmetic intensity of the prefill, and at the same time, since decode has low arithmetic intensity, that means we can schedule more computation, and we are scheduling the exact amount of computation which our machine can sustain, which is nothing but BP1. That means we are actually not hurting the execution time or the latency of one decode. So, latency of one decode is 8 millisecond, and the service level objective is 10 millisecond. We cannot sustain any latency of the decode beyond 10 milliseconds. So, as you can see here, when we push the chunk prefill with a decode, the latency is 9 millisecond, right, which is still less than 10 millisecond, which satisfied the service level objective, and the gain is we are not stalling this request B, right. I mean, we could have stalled the request B and we could have continued with the decode of A, but in that case our throughput would have been lesser, correct. I mean, throughput would have been lesser because although A is progressing, but then we halted B, right. So, the time to first token will be higher in that case. Now, here we schedule B, we let B to start its prefill, but then we did not schedule the entire computation of B or entire computation of prefill of B. We identify here, the authors identified how much computation exactly can be scheduled on top of the ongoing decode of A, so that the service level objective is satisfied. So, that is how this stall free batching in Sarthi is proposed. So, basically they split large prefill into smaller chunks, just enough to consume the leftover compute budget in decode batch. So, remember this term. So, just enough to consume the leftover compute budget, right. In the GPU there is some computation element, right. So, we should not again schedule some prefill or some chunk prefill which is very higher than the leftover compute in the GPU, right. So, that is the main idea of Sarthi. Okay. So, that is the end of today, that is the end of this lecture. In the next lecture we will see more details about the Sarthi. Thank you.